All right, this is the second part of our discussion on the titration of Tums. It's more the calculation side. Remember, both are important to be able to tell the story of what we did. And that was the last slide, or the last video. And this is more of the guts, doing the calculations needed to quantify things. I remember in the last video, I said the key is going to be this determination of the excess HCl that we did in part 2. So I'm going to get to that pretty quickly, but I do want to just talk a little bit about the standardization. How do you exactly do it? So remember, it's the key is the weight. If you know the exact weight of KHP, the more sig figs you can get, the more you get to this molarity. So let's say we had 2 grams of KHP, and I'm going to go ahead and take that to moles. Well, how do I do that? I divide by the molar mass of KHP. So I would take and say, well, I have for 1 mole of KHP, it's about 204 grams of KHP, and you would put that on the bottom, and you would divide 2 by that. And once you get that, you know that the moles of KHP is equal to the moles of NaOH. Well, the moles of NaOH then divided by the volume titrated of that unknown solution, that's not certain. If you know the volume titrated, and you, of course, know the moles already, you can determine the molarity. So we've standardized our KHP solution, and you'll label your NaOH with that particular molarity. And the sig figs is really limited only by the weight, the sig figs in your weight, and also by maybe the volumetric pipette volumetric burette that you used to titrate that solution of KHP. All right. Back to this excess HCl. So we've done our standardization. We know the exact molarity of the NaOH we use for titration of the excess HCl. We say it's 6.5 mils, and we multiply those two. We got this value. Now that's again equal to what this excess HCl is. Let's go back then to number 1, because if I know this, we're going to be able to plug it in here. We have, for certain, at the initial point, an excess of HCl, and we don't know how much of this is excess and how much was used. But because we know the excess, this block, that's dashed, we'll be able to know the block that's shaded in. If we know that, then we'll be able to know the calcium carbonate. And let's just do it using the ICE table. So I know at the very beginning, I have 0.01875. Now, so how'd you get that? I'm going to show you how we got that. We take the 0.025 mils of HCl, that's the volume in liters, 0.025 liters, and we times that by 0.750 moles, molarity times the volume in liters gives me and I've written that out, 0.01875. And we know we don't have the ability just to say, well, this is the same exact, we just take the amount here and divide it by 2, and we know exactly how much of this was consumed. No, because this is an excess, but I can use X. I can say, let's say 2X amount is reacted from this 0.01875, some amount. I know there would be half as much needed of the calcium carbonate. So I have a 2X to X relationship. Twice as much of the HCl, again, needs to be taken in reaction with calcium carbonate. And I know that I would make 2X of the carbonic acid. I'm not really worried about that. But this is key. When that reaction's done, I would have leftover HCl. How much? Well, it would be 0.0. This would be like your change and your final amount at equilibrium. I ran out of space. I'd put that right here. It would be 0.01, and I just rounded it up because of space. 0.0188 minus the 2X would be what I have at equilibrium. Well, I know that's going to be equal to this 0.00367 because it's representing the same thing. This representing the excess HCl left over, and this representing that. So I've set them equal to each other. And let's solve for X, because if I find X, I know the mole amount of calcium carbonate. So to do that, I'm just going to take my math, 0.00367, and I'm subtracting 0.0188 to isolate the x on one side. I'm going to switch the signs. I can do that and make everything positive and divide by 2. And I would get my value, 7.56 times 10 to the third. I'm just going to write it as x equals 0.007565. And that's moles of calcium carbonate. That's what we can represent it. That's how much of it left, and that's how much of it we had. Well, you guys, I hope, are getting pretty quick to see how we can go from moles to grams, because the very thing you have to do is find percent weight at the end of calcium carbonate in Tums. So I may just, with lack of space, say what we can do then with this is multiply it by its molar mass, and that'll give us the weight of calcium carbonate in Tums. And once you know that, I think we have a little bit of space to do that, we can just say that the weight of calcium carbonate is going to be equal to this times the calcium carbonate molar mass. And I'm just going to, I guess, leave it at this 0.007565 times the molar mass, the mass of 1 mole of calcium carbonate. I would multiply that by this mole amount of calcium carbonate, and that would give me the weight. And once I have the weight, the very last thing you'll have to do is divide the weight by the total weight of the Tums and times it by 100, and that'll give you the percent calcium carbonate in Tums. Hope that helps with your calculations, and hope that helps you with your understanding of the Tums lab, or the titration of Tums lab. Thanks. Bye-bye.